Green hydrogen is rapidly becoming the invisible backbone of the renewable energy era, an innovation that doesn't just produce clean fuel but also keeps power grids stable, flexible, and future-proof. As the US and global energy systems accelerate toward higher shares of solar and wind, the biggest challenge is not how to generate green electricity, it's how to store and balance it. That's where hydrogen comes in. Electrolyzers powered by renewables can act as intelligent sponges. They absorb excess electricity when generation is high and scale back when demand rises, converting variability into value. Across Europe and the United States, real-world projects are proving that hydrogen can anchor this new balancing act between renewable abundance and grid reliability. At its heart, green hydrogen through grid balancing is about flexibility. Traditional grids were built for predictable, centralized generation, coal, gas, or nuclear feeding steady baseload. Renewable systems flip that logic. Energy flows fluctuate every hour. On sunny or windy days, generation can exceed demand, forcing curtailment. At night or during calm weather, supply drops and fossil plants are called in. Electrolyzers close this gap by dynamically converting electricity into hydrogen, an energy carrier that can be stored for days, weeks, or even months. This makes them unique compared to batteries. While batteries handle short-term fluctuations, hydrogen covers the long game, bridging seasons and stabilizing both power and industrial systems. Austria was one of the first to show what this looks like in practice. At a steel plant in Linz, a 6-megawatt proton exchange membrane (PEM) electrolyzer was built as part of the H2 Future project to provide balancing services for the grid while producing hydrogen for low-carbon steelmaking. The system's rapid response time allowed it to participate in frequency control markets while supplying hydrogen directly to the industrial process. The success came not just from engineering, but from coordination. Grid operators were involved from day one, ensuring the plant met the technical and regulatory requirements to operate as a flexible grid asset. This lesson has been critical for newer projects around the world, designed for grid participation from the very start. Denmark's High Balance project took that concept further. Located in a region dominated by wind farms, its 1.2 megawatt PM electrolyzer responded automatically to renewable fluctuations. When wind generation exceeded demand, it absorbed the surplus power, turning it into hydrogen for industrial and mobility use. When the grid was tight, it throttled back in seconds, acting as a stabilizing load. The project's reports emphasize the importance of revenue stacking. Earning from multiple sources such as grid services, avoided curtailment, and hydrogen sales. This combination turned an experimental plant into a commercially relevant model for how hydrogen can profitably coexist with renewables. Germany followed with an even larger leap. A 10-megawatt electrolyzer built at Shell's Rhineland refinery, directly tied to both industrial hydrogen needs and the national transmission system. This was the first major European refinery to integrate grid-responsive hydrogen production at scale. Engineers learned to manage complex safety protocols, electrical connections, and system controls inside a live refinery. Lessons that are now being applied to the 100-megawatt follow-up project, Refine Saukasu. Germany's experience underscored that large-scale electrolysis is not just a climate technology, but also a new type of grid infrastructure. Fast-reacting, emission-free, and deeply integrated into industrial clusters. In France, a different experiment unfolded at Fos-sur-Mer with the Jupiter 1000 power-to-gas project. Here, alkaline and PEM electrolyzers work side by side, feeding hydrogen into the natural gas grid after methanation. This dual setup showed how hydrogen could stabilize both power and gas networks while supporting renewable integration. It also revealed the importance of clear safety and regulatory frameworks for injecting hydrogen into existing pipelines, something that U.S. states like California and Texas are now studying closely as they plan blending pilot programs. Across the Channel, the Orkney Islands in Scotland offered another compelling case study. Cut off from the mainland grid, Orkney's wind and tidal generators often produced more power than the local system could handle. Instead of wasting it, the community built small electrolyzers to convert the surplus into hydrogen used for ferries, heating, and vehicles. The project proved that even remote regions could transform stranded renewable energy into usable fuel while relieving grid congestion. The main takeaway was that hydrogen can turn isolation into independence, creating decentralized value from what would otherwise be lost electrons. But Europe isn't alone. The United States has been rapidly scaling its own grid-connected hydrogen efforts, led by innovators like Plug Power, which has evolved from fuel cell manufacturing to becoming a vertically integrated hydrogen company. Plug Power's projects across New York, Georgia, and Texas showcase how green hydrogen can serve as both an industrial energy source and a grid balancing tool. In New York, the company's Genesee hydrogen plant uses hydropower to produce green hydrogen near Rochester, contributing to New York's goal of 70% renewable electricity by 2030. Its Georgia Green Hydrogen Hub, powered by 100% renewable energy, demonstrates how hydrogen can operate in parallel with variable renewables in the southeastern grid, providing flexibility and energy storage. Meanwhile, Plug Power's upcoming Texas facility, one of the largest in North America, is strategically located to tap abundant solar and wind power, turning intermittent generation into a stable supply of hydrogen for logistics and heavy transport. These U.S. experiences reveal a key insight. Grid balancing hydrogen works best when it aligns with both regional renewable profiles and industrial demand centers. In New York, flexible electrolyzers complement hydropower's seasonal flows. In Georgia, they absorb midday solar peaks, and in Texas, they smooth out vast wind variations. Each project demonstrates how the same principle, using hydrogen as a flexible sink for renewables, can be tailored to very different energy geographies. Back in continental Europe, Germany and the Netherlands are writing the next chapter, coupling electrolysis with underground hydrogen storage to achieve true seasonal balancing. In central Germany, a 30-megawatt electrolyzer connected to a nearby salt cavern stores hydrogen produced from excess wind power. The hydrogen can later be withdrawn for industrial use or reconverted into electricity, turning renewables into a dispatchable energy source. In the Netherlands, the Hystock project is developing multiple caverns connected to the national hydrogen backbone, effectively creating a massive energy storage system for the entire country. This concept is now being mirrored in the U.S. Gulf Coast, where developers are exploring large-scale salt dome storage to pair with clean hydrogen production hubs. What unites all these projects, from Austria to Texas, is a growing understanding that hydrogen plants are not standalone assets. They are system assets. Their value multiplies when integrated with energy markets, grid operators, and industrial clusters. In practice, this means building digital intelligence into every project. Energy management systems, EMS, now serve as the brain of these facilities, automatically shifting operation based on electricity prices, reserve market conditions, and off-take contracts. Without such intelligence, an electrolyzer remains just hardware. With it, the plant becomes a dynamic participant in grid stability and market optimization. Location remains another decisive factor. Curtailment, negative pricing, and grid congestion vary from region to region, creating different value pockets for hydrogen. Developers who place electrolyzers near renewable generation and hydrogen users simultaneously achieve the highest utilization rates and lowest transport costs. In Europe, that often means co-locating with industrial zones near offshore wind. In the US, it means connecting to large solar corridors and logistics hubs. In both contexts, understanding local energy market dynamics is the difference between marginal economics and long-term profitability. The business model behind these projects is also maturing fast. Rather than relying on a single source of income, developers now combine three streams: grid services, frequency control and reserve markets, hydrogen sales to refineries, transport, or industry, and energy storage or arbitrage, buying electricity when it's cheap or negative, selling hydrogen later. This stacked revenue approach transforms the economic landscape for hydrogen plants. It spreads risk and aligns with investor expectations for diversified, resilient returns. Banks are beginning to recognize hydrogen's reliability as a flexible load, especially as more operational data validates uptime and efficiency. In parallel, policy frameworks are evolving. Europe's Renewable Energy Directive and the U.S. Inflation Reduction Act IRA, both reward hydrogen projects that use renewable electricity and demonstrate verifiable carbon reduction. The IRA's production tax credit 45V, for example, incentivizes developers to operate their electrolyzers flexibly, using renewable power when available, to minimize carbon intensity. That policy, combined with grid balancing applications, is propelling the U.S. hydrogen industry toward parity with leading European markets. For developers, the message is simple. Integrating with the grid and operating dynamically doesn't just stabilize electricity, it also maximizes financial incentives. Technology selection continues to shape outcomes. PM electrolyzers dominate where flexibility and fast response are required, while alkaline systems serve in steady, high-load environments. Many next-generation projects are combining both to create hybrid platforms that can chase market signals without sacrificing efficiency. Meanwhile, emerging technologies such as solid oxide electrolysis, SOEC, promise even higher efficiency when paired with waste heat from industrial sites, an opportunity the U.S. Department of Energy is supporting through its Hydrogen Hubs initiative. This nationwide program aims to link production, distribution, and end use across clusters, embedding grid balancing hydrogen as a pillar of America's clean energy transition. Storage remains the strategic enabler. Without sufficient hydrogen storage, electrolyzers can't freely follow grid signals. Small-scale systems use pressurized tanks for hourly flexibility, but the future lies in geological storage, salt caverns, depleted gas fields, or aquifers that can hold hydrogen for months. This is where the U.S. has a natural advantage. Vast underground formations along the Gulf Coast and Midwest could support gigawatt-scale hydrogen storage integrated with renewables. By pairing these resources with the country's expanding transmission and hydrogen pipeline infrastructure, developers can build projects that balance not only the grid, but entire energy systems. From all these experiences, a few universal lessons emerge. First, early engagement with grid operators is non-negotiable. The most successful projects, whether in Linz or Texas, were designed around grid participation rules from day one. Second, digitalization is key. A strong EMS and forecasting algorithms can make the difference between profitable flexibility and costly downtime. Third, location defines economics. Sit where renewables are abundant, electricity is cheap, and off-takers are near. And finally, storage turns flexibility into stability, enabling hydrogen to bridge hours, days, or even seasons of imbalance. For developers and investors, green hydrogen through grid balancing represents both a business opportunity and a climate solution. It turns volatility into revenue and emissions into progress. It connects renewables with hard-to-abate sectors, stabilizes regional grids, and unlocks new energy ecosystems. As Plug Power and other innovators continue scaling up across the United States, the technology is moving from pilot projects to a continental infrastructure layer, one that complements the growth of renewables and reinforces energy security. In the coming decade, expect hydrogen to evolve from a niche decarbonization tool into a cornerstone of grid architecture. It will coexist with batteries, complement pumped hydro, and support industrial decarbonization all at once. The pioneers in Austria, Denmark, Germany, France, and now the US have proven the blueprint works. The next wave will simply scale it up, linking flexible hydrogen production with advanced grid operations to create the backbone of a clean, resilient energy economy. If you're ready to explore this future and learn how to design, model, and finance your own hydrogen project, the Green Hydrogen Development and Financing course at h2hub.renewable.com offers everything you need, from feasibility modeling to financing frameworks. It's time to move from watching the hydrogen revolution to building it.